Hi everyone, today we're going to be looking at the central limit theorem. Have you ever wondered what's the probability of you being born in Mexico? That's right. Or even the probability of finding your best friend and being besties. Or even the probability of being born. And think about this, what's the probability of all this happening to you in one lifespan? The central limit theorem tells us from all this randomness, from all this chaos, from all this probability, there is order from chaos. There is organization. There is a pattern. And we could see this from a graph if we do this procedure that statisticians use. Okay, so let's make something hypothetical. Let's pretend that there's 100 students taking an exam. And the score is 1 through 10. 10 being amazing, you did spectacular. 1 being you did terrible, you failed. But I mean, at least you tried your best. Now this is a discrete probability distribution function. Don't be scared, there's nothing to be frightened of. This just tells us that from the 100 students that took the exam and from the 100 students that scored 1 through 10, this tells us the likelihood of selecting a kid that scored a 4 or a 3. So for example, if you were to just pick a kid at random, right? You just grab him from the crowd. It's very unlikely he scored a 3, a 6, or a 7 based on this graph. Now, let's say you picked another kid. It's very unlikely he also scored a 3, a 6, or a 7, but it's very, very likely. The probability is higher that he scored a 4 or an 8 or a 9 based on this graph. So that's all this is telling us. It's basically just storytelling for mathematicians. Okay, so what are we going to do with this information? Well, we're going to just select some number of students. In this case, we're going to select 6 students. So from the 100 students that we have that scored 1 through 10, we're going to collect 6, and then we're going to write down what they scored. Okay, so here are 6 students that have their scores, and I named this group S1. Now, our first student got a 2, unfortunately. Our second student got a 4. Our third student got a 4. The other student got an 8. The other student got a 9. And then lastly, that student got a 5. Okay, perfect. So we did this one time. Now we have to do it a bunch of times. In this case, I did it up to 4 times. But ideally, you want to do it as many times as possible, the same process. So again, we just picked some kids at random. In our second group of students, we see that, there's some kid got a 9, the other kid got a 9, the other kid got a 5, a 4, a 4, a 4, and that's just our second group. So we move on to our third group, and the same process happens. We select 6 students, we record their scores, and we do that up until 10,000 groups, right, of students. Okay, so what's next? Okay, now we're just going to find the mean for each group of students. So yes, we're going to find the mean for S1, we're going to find the mean for S2, S3, all the way to S10,000, which I was too lazy to do S10,000, but you get the idea, right? We find the mean, and the mean for the first one is 5.33. The mean for the second one is 5.83, and so on and so forth. We get 4.5 for the third group, and for the fourth group, we get 5.16, right? Pretty easy stuff. To find the mean, all you got to do is just add all the numbers and divide by the number of students that we have. In this case, it's 6. And that's how you find the mean, right? So you have the mean for all these group of students, S1 all the way to S10,000. What do you do next? Well, we're going to graph it now on something called a frequency distribution. So as you can see, I did it for our first 2 groups, right? First 2 groups of students, because I was too lazy to do the rest. But you get the idea, right? We did our first 2, and this is just the mean. And now we're gonna do the rest. We're gonna do all the way to 10,000, and we do it. And what do we get? Bam! We get this shape. We get something called a normal distribution, and that's what the central limit theorem is all about. So this looks good. This is a normal distribution, but let's make it closer to a normal distribution. How do we do that? Well, it turns out that if we increase the number of samples that we had, remember we had 6, but let's say we turn it to 30 number of samples. That means that instead of selecting 6 students out of the 100, we selected 30 students out of the 100 and recorded their test scores. So we did, we select our 30 students, and we do the same process again. We find the mean for each group, and we don't just do it 10,000 times. Let's say we do it more than 10,000 times. Instead of getting 10,000 groups of students, we get, I don't know, maybe 50,000 or close to infinity or whatever, a gazillion, right? If we do all that many times, then we will get something closer to a normal distribution. So what can we take out of all this? Well, if we increase the sample size, remember ours was 6 in this example, and we did it to 30. If we increase that, and if we also increase our group sample number, remember, we originally had 10,000, but then I mentioned to you that we're going to increase it to 50,000 or even infinity, right? The point is that we increase that number. Then we get something closer to a normal distribution. And that encompasses the central limit theorem. So I want to end with this. Even with the most uncertain processes, there's always going to be a predictable center. That's what the central limit theorem tells us. That from all this chaos and randomness, there's beauty and harmony. Why does this happen? I can't tell you why. That's a question for another video. But I hope you enjoyed the video. Bye, guys.